Hello everyone. This week we will study the Pigeonhole Principle. So we first state the principle in its simplest form, which is I call it a theorem, but I will not give the proof. It's very easy. So if n plus 1 objects are distributed into n boxes, then at least one box gets at least two objects. Okay, we look at some applications. So first, we know that among 13 people, there always are two people that had birthdays in the same month. Okay, next example. So assume we have a jar contains a mixture of black and blue socks, and that you are pulling number of socks from the jar without looking or randomly. And the question is, what is the minimal number of pulled socks required to guarantee a pair of the same color? So here actually we assume there's no left or right for a sock. Okay, so the answer is 3. As soon as you have 3 socks, at least 2 of them have the same color. Since there's no right and left for socks, they can guarantee a pair. Okay, and then a little bit different is, suppose we have jar, we have 10 pairs of gloves, and what is the minimal number of pulled gloves required to guarantee a pair? So here we still assume we pull out gloves randomly without looking. So keep in your mind that pigeonhole principle always applying to the worst situation. From the worst situation, we still want to conclude some good stuff. Therefore, we apply the pigeonhole principle. If you can do choice, of course, for example, for the gloves problem, if you can look, you can just take out 2, which guarantee a pair. But this is another purpose of the pigeonhole principle. Pigeonhole principle applies to the worst situation and to guarantee some good properties. So here, at least you need 11 gloves. And then let's look at the following proposition. So given integers a1, a2, am, so m greater than or equal to 1, and then at least one of the sums ai plus 1 plus ai plus 2 plus all the way to aj is divisible by m. And here I and j are arbitrary between 0 and m. I is strictly less than j. Okay, then the idea is to apply the pigeonhole principle, and from the proof you will see the key point for the pigeonhole principle is to construct the pigeonholes. And sometimes there are natural pigeonholes. Sometimes you need to work really hard to get it. Next time when we talk about Ramsey theorem, probably we will have a better feeling of that. So proof. So instead of ai plus 1 plus all the way to aj, we consider the summation from a1 to aj. a1 plus a2, a1 plus a2 plus a3, a1 plus a2 all the way to aj, and finally a1 plus a2 plus all the way to am. Okay, so totally you have m sums here. Okay, and if any of these numbers is divisible by m, we are done. You just take I to be 1. And otherwise, m sums take only m remainders when divided by m. So that is 1, 2, all the way to m minus 1. Those are the only possibilities for the remainders, because we assume there's no numbers divided by divisible by m. Okay, then you see there are nature pigeonholes. You view 1 to m minus 1 as pigeonholes. View remainders and a1 plus a2, a1 plus all the way to am as objects. Then we can apply the pigeonhole principle. So by pigeonhole principle, there are I less than j greater than 1 less than equal to m, such that a1 plus all the way to aj has the same remainder as a1 plus ai. That is, so apply the pigeonhole principle. The direct consequence is that there's at least one remainder such that two of the summations corresponding to it. So we take ij as a corresponding summations. Okay, mod m. And since j is strictly greater than I, then if you subtract right from the left, you have ai plus 1 plus ai plus 2 plus aj minus 1 plus aj has a remainder 0 modulo m. So this is just divisible by m. Okay, next, let's prove the Chinese remainder theorem. So recall that actually the previous proposition is not so commonly used. It's just for you to have a good understanding of pigeonhole principle. But the following Chinese remainder theorem is widely used in number theorem and combinatorics and a lot more other fields. And actually they lead as a guiding principle also for some other complex analysis, complex geometry phenomena. Chinese remainder. So let m and n be relatively prime, positive integers and let a and b be integers such that a is between m minus 1 and 0 and b is between 0 and m minus 1. Okay, then there is a positive integer x such that the remainder when x is divided by m is a, and the remainder when x is divided by n is b. Okay, before we prove this, let's first do some remark. First, what do we mean by prime? Relatively prime. That means m and have no common factors greater than 2, greater than or equal to 2. So you cannot have some common primes as their factors. And then what is the conclusion? It's not so easy to remember the result in this form. So first, let's transform the last sentence in the following way. So first, the remainder of x divided by m is a means x can be written down as pm plus a. where p is an integer. And similarly, for the second half, we have x is qn plus b, where q is also an integer. Okay, so this is exact form for the statement, but most of the time p and q are not important. Therefore, we prefer the following following form. So x has remainder a when mod m, x has remainder b when mod n. So let's denote this as star. Then the Chinese remainder theorem is same as the following statement. If mn is coprime or relatively prime, mn greater than or equal to 1, then star has solutions for all a and b. Okay, as soon as m and n are coprime, the number of a and b are not important. So this is kind of some sufficient condition to guarantee a solution, which is very important, because if you look at the equation, it's overdetermined. You have too many variables instead of the too many equations than the variables. But of course, here you don't have the equality. You have equality modular some numbers. It's still a differential equation. And next remark is this is still not the most general form. A slightly more general form will be you have m1, m2, m for example mk, and here you don't assume each pair is coprime. You only assume there's no common factors for all of them. Okay, and then there's a solution for the following equations. This is just like you prescribe the remainder for some number. Okay, we will now prove the general form, and we focus on the proof for the simplest 2 primes case, since the idea will be similar. Okay, now let's consider A, m plus A, and 2m plus A, m minus 1m plus A, and noted that they have remainder, they have the same remainder A when divided by m. Okay, now we claim that each of these integers has a different remainder when divided by n. And see, suppose claim is true, then you have here also you should remark there are n numbers, and when divided by n you have n remainders from 0 to n minus 1, and if you have n numbers put it into the n boxes and no two of them put into the same boxes, then you can conclude each remainder correspond to some number im plus a. Okay, in particular, there's some number lm plus a, which is divided by n. Okay, so this claim is suffices to conclude the theorem. Therefore, we first prove the claim. Okay, suppose we prove by contradiction. Suppose there's suppose we have two integers I and j between 0 and m minus 1, such that these two numbers have the same remainder when multiplied by n. And you subtract left from right or right from left, you conclude j minus I times I m is divided by n. Equivalently, n is a factor of j minus I times m. But since n and m is coprime, or the greatest common factor is 1, then n must be a factor of j minus I. However, j minus I is greater than or equal to 1, less than or equal to n minus 1, in particular less than n, which is a contradiction. So that means n, this is because n cannot be a factor of some non-zero integer which is smaller than n. So if you want a statement, if let's see, x is a factor of y, and y is different from 0, then x is, the norm of x is less than or equal to norm of y. Okay, and since the contradiction, we conclude that the proof is true. Sorry, this claim is true. Okay, then each of the n numbers 0, 1, n minus 1 occurs as the remainder for 1 O A m plus A m minus 1 m plus A. And in particular, there is an integer L in between 0 and m minus 1 such that Lm plus A has remainder B when divided by m. Okay, then Chinese remainder theorem follows. Okay, so we make several remarks. So first, here we actually use some variations of the pigeonhole principles. So the first variated form is if n objects are put into m boxes and no box is empty, then each box contains exactly one object. And 2, if n objects are put into m boxes and no box gets more than one object, then each box has an object in it. So actually we use the second form, second variation in our proof used here. Okay, and actually 1 and 2 kind of related. If you know a little bit PDE, or you are going to learn PDE later, in PDE, for example, when you study some Laplacian U equals F, or more complicated second order differential linear differential equation, LU equals F. L is a differential operator. And sometimes we want to say it has a solution. That means just like the first case, each box contains a solution or no box is empty. But usually it's very hard to prove, and you have another called the Pigeonhole Principle, which says kind of 2 is equivalent to 1. So to prove there is a solution for all condition F, it is equivalent to prove that du equals 0 has a unique solution, or LU. So the uniqueness is just a second case. Okay. So of course the statement will be more complicated. You need to specify what is the domain you are considering, what is the space for you. You are in smooth category or in W2P or integrable function spaces, and what is the restriction on F. But the idea, I think, is similar. Just transform some onto property into some injective property. Okay, now we're in good shape to introduce some formal language. Remember previously we always talk about what is a bijection and one-to-one corresponding to each other, but I never give you some rigorous definition. So here we will define it in a rigorous way. Given sets x, y, and function f from x to y, and f is called one-to-one injection if for all x prime in the bigger space X, such that X different from X implies Fx is different from Fx prime. That is, if you choose different elements in X, the image is automatically different. Then the map is called injective. F is called onto or surjection if for all element in Y exists an element X such that Fx is Y, and F is called bijection if F is both injective and surjective. Okay, then if you look at the picture, suppose you have map X from X to Y. Then injective means there's no two elements in X maps to the same element in Y. This is not allowed. And similarly, for a surjection or surjective map or onto map, for each point Y in Y, there's some point X in X such that there's a map, such that Fx is Y. Of course, you might have many different Y's, just like you might have many different solutions, but they all give you the same image. So surjective just say for all Y there exists X. Okay, so in this language, we can abstractly formulate the pigeonhole principle as follows. Yeah, we do all kinds of variation of pigeonhole principle, just give you different feeling of the principle. When you apply it, you should choose a form you'd like. Yeah. So suppose x, y are finite sets. F is a map from x to y. And if the cardinality of x is greater than y, then we say F is not injective. That is the original pigeonhole principle, which means there must be at least one point, one boxes contains at least two objects. So this is meaning as not injective. Secondly, so if x and y has the same cardinality and F is injective, then F is surjective. And similarly, if x equals y, if the cardinality equal and F is surjective, then we have F is injective. Okay, next we turn to another application. So before that, we define what is called a decreasing subsequence or increasing subsequence. For a sequence A1, A2, AN by a subsequence of length K, we mean AI1, AI2, AIK. So where the indices I1, I2, IK are from 1 to n and increasing. So this is called a subsequence. Now, the subsequence is decreasing. It's called decreasing. If AI1 is greater than or equal to AI2, which is greater or equal to AI3, all the way down to AIK. And similarly, the subsequence is called increasing if AI1 is less than or equal to AI2, less than or equal to all the way to AIK. Okay, now let's look at some examples. So first example, suppose n is 4, and the sequence you have is 1, 3, 2, 4. This is a sequence. Okay, and then let's consider its decreasing and increasing subsequences. And increasing subsequences. And we divide into cases by the length. So for the decreased sequence of length 1, then of course you have 1, 3, 2, 4. And similarly for increasing subsequences, you also have this case. And for decreased sequence of length 2, you cannot start with 1. Okay, and if you start with 3, the next one must be 2. And that's the only possibility. But for increasing subsequences, if you choose 1, the next you can choose 3 or 2 or 4. Okay, and if you choose 3, then you can have 4. If you choose 2, then you can also have 4. Okay, for now, let's look at decreasing subsequences or length 3. Then there's no such subsequences. But for increasing one, you have 1, 2, 4. Okay, and for decreasing subsequences or length 4, you don't have any, and neither for increasing ones. Okay. Next, we will stay very important theorem due to Elders and Daggers, 1935. Okay, actually, this not the purpose of their paper. Their purpose their paper studied the complex polygon or complex region, whatever. But this probably the key lemma used in their paper. So it says that given an integer k greater than or equal to 0, let n to be k squared plus 1. Then each permutation of 1 to all the way to n has either at least one increasing subsequence of length k plus 1, or at least one decreasing subsequence of length k plus 1. So the proof is not so easy. They give an elegant proof. Probably you will have another elegant proof. But for me, I tried something very naive and which doesn't work. But I would like to show you why my naive method doesn't work, and so that you can appreciate their proof more. No working plan. So my naive thinking is for k equals 0 or 1, you can easily do that, and then probably you can do some induction on that, because if you assume theorem holds for n equals k squared plus 1, we want to prove theorem when n equals k plus 1 squared plus 1. Okay, then you see you have k plus 1 squared plus 1 minus k squared plus 1. You have 2k plus 1 more elements in your sequence, and you only need to enlarge the increasing or or the decreasing subsequences by length 1 by one element. How to enlarge a subsequence decreasing or increasing subsequence of length k by one element. And if you naively do the following, you take the first k squared plus 1 element and leave out the next 2k plus 1 element. Then from this, you can get decreasing or increasing subsequences of length k or length k plus 1. Okay, then can you choose some element here such that this is less than the so let's call it, okay, let's call this last one green. So can we find yellow green dots, a green circle such which is less than or equal to the purple one? So that's my naive thinking, but of course it doesn't work. And if you compare this bad idea with their proof, you will see the key point is I didn't incorporate decreasing and increasing. So here from my plan, you will see there's no relation between decreasing and increasing. But in their proofs, the decreasing and increasing serves as very subtle. They have very subtle relations. Okay, I will not talk about the plan more because it doesn't work. Okay, so now let's turn back to their proof. So suppose there is no increasing subsequences of length k plus 1. Oh, okay, so here I use a different notation. Okay, let's use length less n plus 1. Okay, let's first fix the notation. You have too many notations, too many variables, n, k, blah, blah. So let's consider a permutation. Consider a permutation. Okay, sorry about that. Okay, I would rather still use k. Oh, then I don't need to change the notation. Suppose there is no increase in subsequence of length k plus 1. Okay, then for each m equals 1 to all the way to k squared plus 1, let Lm be the length of the longest increasing subsequences that begins with AM. Okay, let's see the permutation is. Or the 4 sequences. A1, A2, all the way to AN. Okay, so here we let LM be the length of the longest increasing subsequence that begin with AM. And I will explain this a little bit later. So since 1 is less than or equal to LM, less than or equal to N, or less than or equal to K. So this is by the assumption that no increasing subsequences of length K plus 1. Therefore, you have upper bound for LM. Okay, and here M is a number from 1 to 3 all the way to K squared plus 1. Okay, now notice that then L1, okay, so consider the numbers L1, L2, all the way to L K squared plus 1. And then what can you conclude? Then we have that then there are at least K plus 1 of them are equal. This is by Pigeonhole Principle, which is also very easy to prove. Actually, we use a little bit different version of the Pigeonhole Principle, but it's also easy to prove. Suppose otherwise we have only K times K objects instead of K squared plus 1. Because LM, so those numbers actually take values from 1 to K. Therefore, K squared plus 1 divided by K is greater than K. So you have at least K plus 1 of them take the same value. Okay, then let LM1 equals LM2 equals LM K plus 1. So without the loss of generality, we can assume that where 1 is less than M1, less than M2, all the way less than MK plus 1, less than or equal to K squared plus 1. Okay, then the most important claim, which I cannot incorporate in my proof, is that so far we only consider the increasing subsequences, but the interesting thing is if you look at the element in the sequences with indices m1, m2, mk plus 1, we have the decreasing subsequence. So this is very astonishing, and which is really the key observation. I think most of the time, the tricky proof of mathematics come from the following idea that you only assume one thing, but very luckily you get back two. So here you only assume they only care about the increasing property, but we are very lucky. From the increasing properties, we derive a nature decreasing subsequences. So this is just by luck. Okay. So, and actually this leads to the final proof. Okay, as soon as I tell you this, it's very easy, because otherwise we have certain, oh sorry, I should use black pen. I have certain AMJ is strictly less than AMJ plus 1, where J is from 1 to K. Okay, then take the longest increasing subsequence starting from AMJ plus 1, then we will have AMJ plus 1. So let's see, AJ2, AJ3, all the way down to AJ LMJ plus 1. Okay, so this is the longest increase in subsequence starting from AMJ plus 1. Okay, and why this is because the length is LMJ plus 1 by the assumption. So here, actually what we are doing is interpreting this choice. How do we choose? So we're starting from, for example, we start from AM and look at all the increasing subsequences. So we AM2 prime, AM3 prime, blah blah, such that it's increasing, and also M is strictly less than M prime less than M2 prime. Oh, sorry, M3. Blah blah. And then you take the largest possibility. Okay, and now you consider AMJ less than AMJ plus 1 less than or equal to AJ2 less than or equal to AJ. So here you have the indices also have increasing property less than AJ LMJ plus 1, which means length LMJ must be greater, at least as large as LMJ plus 1 plus 1, which is a contradiction. Because at the very beginning, how we take such indices m1 to mk plus 1, we assume that they are equal. Okay, so you have contradiction. So this is a simple for contradiction. Okay, then we are done. You hit on the wall. Okay, so then look back the whole proof. If you don't have increasing subsequence of length k plus 1, then you must have a decreasing subsequence of length k plus 1. Then we complete the proof of theorem. Okay, let's turn back to the pigeonhole principle. So we do the following remark. So actually here we use a slightly stronger version of pigeonhole principle. That is, given n boxes for 1 less than I, 1 less than n, take integers qi greater than 1. And if we put q1 plus q2 plus qn minus n plus 1 objects into these n boxes, then one of the following is true. First, box 1 gets at least q1 objects. 2, box 2 gets at least q2 objects. And blah blah to n. Box n gets at least qn objects. So in the proof of Daggers, actually we use a strong form by taking q1, q2, qn as the same number k. About proof. Okay, and next, let's talk about little bit about the following up of the history of Daggers or the background. So actually, this is called Klein Daggers problem, and elders also call it happy ending problem. This is because later on Klein and Daggers get married because of this problem. The problem was first raised up by Klein, and then Daggers wrote a paper together. So in Daggers' paper, they actually prove the following statement. Any set of 5 points in the plane in general position has a subset of 4 points that form the vertices of a convex quadrilateral. And this actually leads to Ramsay theorem, which is a branch of combinatorics nowadays. And they conjecture that the smallest number of points for which any general position arrangement contains a convex subset of n points is 2 to n minus 2's power plus 1. It's still open according to the Wikipedia, and many people work on the upper bound for it. There's some upper bound for it, and if you like, you can choose this as your reading project, reading report topics. You just choose some of the following up papers to study the idea of more subtle proofs. Okay, I will not talk about this topic further, because then it involves a lot of advanced tools like Fourier analysis or very subtle combinatoric eliminations. Okay, let's turn back to the pigeonhole principle. Actually, the pigeonhole principle is much more widely used than we thought. For example, we can deal with the following problem. So suppose you have 10 points placed on a unit square. Then we claim then 2 of them are closer to each other than 0.848. And as we said before, the key point is always to construct the pigeonholes. If you you divide the unit square equally into 9 small squares, and you will see at least 2 of the points, at least 2 points will be in the same smaller square. And if you look at the smaller square, then the largest distance between them will be the diagonal. So this is 1/3 times square root of 2, which is less than 0.48. Okay, and next let's look at another tricky problem. Though these two problems are not as nature as or as good as the previous elders Zacharias problem. So how to tell a problem good or not? Good problems leads to, or the solution of good problems open door for a larger or wide picture of mathematics or the research field. People get more and more excited, interested in that topic. Bad problems just the end of the study. After the study, you get nothing, and people forget about that. There are quite a lot of hard problems in the history of mathematics involved people's efforts, but later on just get forgotten. But as a researcher, before you do it, you cannot tell which one is good, which one is hard. You can tell only by your own taste. It helps you to decide which role you are going, but it cannot guarantee the role. So if you look at interviews of many great people, great mathematicians, great scientists, they will always tell you the taste is very, very important for a scientist. And I remember once Chen Yang said, you have two same level students entering the graduate school or entering after the PhD study, but later on, after 20 years, they have huge difference. Why? Not because they have different abilities or whatever, or personalities, just because they choose different roles. And one field just get more and more interesting, the other field gets die. So that decides the future of two people. I think these philosophies, it applies to not only science but also your career. So I would like to open your mind and get well prepared. Be very careful what you are doing in the future. Not because it's popular, or some other mathematician also said in a very extreme way that what is a hot topic in the next 10 or 20 years, that is tangential to the current hot topics. Okay, so let's finish up the lecture by the following example. So suppose a student have 37 days to prepare for an exam, such that the following rules are obeyed. So each day she starts with certain numbers, integer numbers, hours. That means she doesn't do 1.5 hours or whatever. She always do 1 hour, 2 hour, 2 hours or 3 hours, blah blah. Secondly, totally you have 60 hours. And lastly, at least 1 hour per day. Then the claims is, then there exists a sequence of consecutively days during which she studies exactly 13 hours. Okay, we first transform the problem in some mathematical form. So suppose let's denote hours studied each day by H1, H2, H37, and then the condition you have is each of them are positive integers, and the summation is 60, and we want to prove exists indices n and m between 1 and 37, such that summation from n to m hi is 13. Okay, and let's just construct objects and pigeonholes. So the objects we have is b1 plus b2 plus bj, j from 1 to 37, and the union the elements b1 plus b2 plus bj plus 13, I from 0 to 36. So those are objects. This problem a little bit different. We construct objects more extensively than the pigeonholes. Then totally you have 34 objects. And noted that under the above condition, we know that minimal of the 34 objects, the minimum value is 1. Because the minimum of the second of the objects in the second category is 13, and in the first category is B1. B1 at least 1, so the minimum is 1. And the maximum of this 74 objects is 32. Why? Because for the first category, it's always bounded by the total hours. I from 1 to 13, HI is 60. And the second one is bounded by the total hours minus H37 plus 13. Okay, so this is less than 72. Therefore, if you construct pigeonholes as all the way to 72, then by the Pigeon principle, we can conclude there are two objects take the same value. But this is not done yet, because you have the possibility that two hold the, so let's call this is first category, second category. So, question, can such objects be in the same category? Then we are in trouble. But from the construction, the subtle construction, you can see these two cannot be in the same category, because each of these each is different. In first category, each element in first category is different, and each category is different. Each element in the second category is also different. So the answer is no. Then we are done. So I will not, oh sorry, this is, you have few more steps to complete, but basic idea is like this. Okay, I will stop here. Next time we will talk about the Ramsey theorem.